In this video, we study implication of propositional logic and how to handle it in Lean. We start by assuming that A and B are two propositions. And we first think about how to prove a proposition that is an implication. Recall that in the past videos, we usually assumed having a proof of a proposition, say A, by including it as a variable. And this variable then shows up in the context here when we prove something else, for instance, B. Yeah. So whenever we assume a variable, here we assume that we have a proof of A, and we can use this proof of A when we set ourselves a goal, for instance, proving B. Implication is now, the purpose of implication is to make sure that we do not have to assume things given as variables. Instead, we can just write statements as A implies B. Namely, suppose we want to prove A implies B. Let's comment this out for the time being. Suppose we want to prove a proposition, the proposition A implies B. Well, whenever we see a goal like this, one proof strategy is to assume we assume having a proof of A, and then it remains to prove B. And the effect is exactly the same if you compare this goal now to the goal that we had up here. It's exactly the same. Up here, recall, we had assumed having a proof of A, and then we remain with proving, we are tasked with proving B. And when we want to prove A implies B, we do one proof step, which is to assume having a proof of A, and it remains to prove B. And in the proof of B, we can, of course, use the proof of A that we have assumed. So this is to show that the effect of this keyword, of this proof step, assume, is exactly as if we had assumed having a proof of A using the variable keyword. Yeah. So the goal state here is exactly the same at this point as it is at this point here, where we have assumed before starting the proof having a proof of A. The intuition is that in order to prove an implication A implies B, so we are reading this inference rule backwards, in order to prove that A implies B, it suffices to prove A. It suffices to prove A here, where in the proof of A we can assume that we have, where in the proof of B we can use an assumed proof of A at any time we want. And so again, in an interactive situation, this looks as follows. When the goal is to prove A implies B, then we make one proof step that assumes we have a proof of A, and then the goal becomes smaller. The goal becomes just B, but now we have an additional tool at our disposal, namely a proof of A. Okay, now suppose we have a proof of A implies B. How can we use it? That's the elimination principle. Well, that's actually very simple. Think of the proof that A implies B as a function that gives you a proof of that gives you a proof of B if you feed it with a proof of A. And this is just written also as function application. So if F is a proof of A implies B and A is a proof of A, then F applied to A is a proof of B. In an interactive scenario, this would look as follows. Suppose we want to prove B. goal is to prove B. Let's make it such that that these assumptions show up in the statement. Suppose we want to prove A, and we have a proof of A implies. Suppose we want to prove B, and we have a proof of A implies B. Then we just use this proof, F, and that sort of goes backwards in this implication. Our proof, our goal statement, our goal now has changed from B to A. So we have gone backwards in the implication, and instead of needing to show B, we now need to show A. And this can be simply done by using A.